All right, welcome everyone. Let's make sure that everybody can hear us. Let's see. Okay, all right, I think we are good to go. Hi everyone. My name is Anurag Purwar, and I'm joined here with my colleague Amiya Khale. I'm a professor of mechanical engineering at Stony Brook University, and I have been going to the Maker Faire for a very long time. In fact, we have always had a presence in the Long Island Explorium Maker Faire for several years now. It was canceled, of course, this year for the obvious reasons. So I'm super excited to be here virtually with everyone with something really very different. This is going to be a hands-on virtual workshop, and both Amir and I are very excited to bring this to you. Uh, so Amaya is from Mechanismic. It's a New York State startup, and I'm part of Mechanismic, and Amaya is also part of Stony Brook because he graduated from Stony Brook not too long ago. Amaya, you want to say anything to our attendees?
Yeah, just want to welcome everyone to this workshop, and it's going to be a really interesting experience for everyone here to know about how robot motions are designed. And Dr. Purwar has immense experience in this field, and he'll be guiding you through this quite wonderfully. So just make sure you participate, and it will be really fun.
Good. I see we have basically only 4 attendees, so we can really keep it very hands-on and we can answer their
Mhm.
questions. So that should be fun. Okay, all right. So the title of our workshop is Magic with MotionGen, Learn to Design Robot Motions. So this is quite a mouthful, but I assure you, when you start working on designing these robot motions using the app called MotionGen, you will find that it's really not that bad. Okay, all right. So with that, let's get it started. So first thing is, I would like you guys to take a moment to introduce yourself in the chat. Just include your full name, if you feel comfortable doing that, your location where you are, your role, if you're a student, you're a teacher, you're an admin, and if you come from any school or organization. Look at the chat just in a few seconds. Okay. Oh yeah, there could be. So Doug, who's our moderator, is telling us there could be a lot more on YouTube stream. Actually, that's something that I did not realize at all. So that's great. So welcome, Jack. Jack is a student. Let's hear from Dennis, Maggie, and Anil. Dennis, are you here? Okay. All right. Oh, Anil is here. Well, he's a grandfather. We know Anil. Welcome, Anil. Good to see you here. Doug himself is a tech teacher in Buffalo. That's fantastic. All right. Okay, Dennis is in Colorado. He's a part-time maker. Fantastic. That's great too. Okay, the only person we have not heard from so far is Maggie. It's from Maggie here. Okay, Jen, Maggie, and Catherine from California. Northern Grandkids Tunnel. Oh, welcome, welcome, Jen. Welcome, Maggie. Welcome, Catherine. All right, so let's get it started. And I'm sure there are a lot more people on YouTube stream who we don't know about, but hopefully Doug will find some time to maybe copy their introductions and just paste it here in the chat so we can see who they are. All right. So this is an interactive sessions, and I'm going to be asking you guys to complete several design exercises in a browser, and Google Chrome works the best. So if you have Google Chrome on your machine, Windows or Chromebook, or even a Mac machine, that should be fine. I will give you the URL for the website where you need to go, where our app is hosted, which is what you will be using today to do these design exercises. Again, while I'm talking, it's very hard for me to monitor the chat, so both Doug and Amaya will help me if there are any questions that I need to answer right away. Otherwise, we can always take some time to answer them at the end. But since this is supposed to be an interactive session, I would expect that you would have questions, and you should feel comfortable to ask those questions as and when they arise, okay? All right, so the first thing is that you should go to this URL that you see at the bottom of this slide, tinyurl.com/makerfair2020. And I will also, just escape it and put this URL into, let's see, into the chat, so it'll be easy for everybody to copy it. All right. Amaya, if you could do that too. Okay, I see Doug has already done that. That's fantastic. So I don't have to do this anymore. So over here, yeah, you can do that. You can if you go to this URL, you will find several files. Most important one is the PDF of this presentation. So this presentation that I'm giving right now, there's a PDF of it available. So download that, and that way you'll be able to follow along with me, and you will also be able to access these URLs without having to remember as to what they are. Okay. All right. So hopefully everybody has this address now, and they can get the PDF. Okay, so here's a very brief outline. I will talk a little bit about, as to where we are coming from, and why we are doing this, and what MotionGen Pro is, and what this is really part of. Then I'll talk a little bit about how we can do what we call mechanism design simulations. Okay, so mechanisms are generally part of any robot or any machine, and in fact, that's where the heart of a machine lies. That's where the heart of a robot lies. Physical prototyping of the robots is something that's another interesting topic that we will discuss again very briefly, because you're not really going to be doing any physical prototyping in this session, but you will see as to how you can do physical prototyping of robots and machines using a brand new robot kit called SnapExo that I have been involved in developing and now trying to bring it to the market. And then we will do 4 exercises using MotionGen Pro, the app that runs in the browser. And these are fairly simple and interesting, as at least we think, interesting exercises. And then we'll end with a Q&A and a survey that you can fill out, and a chance to get a robot kit. Okay. All right. So with that, let me give you a little bit of I don't know. Let me start with an apology, because I'm going to take you back like almost 250 years ago during the Industrial Revolution time, when really people were designing interesting machines and mechanisms that were making people's lives simpler. And then I'm going to bring you, back to the modern age, where we talk about machine learning combined with machine design, the kind of work that I'm doing, more recently. So it's going to be a bit of a roller coaster ride, but hopefully, you will stick around and find this whole thing interesting. So here's a very, very basic question, right? So when you look at this mechanism, this is part of James Watt's steam engine, right, which he invented more than 200 years ago. And one of the biggest question when he invented this mechanism was as to how he did it, right? Because if you look at it, you see so many moving parts in here. You see there is, a blue link number 2, that's doing a pure rotation. And then you see a pink link called link number 8 that's doing a straight up and down motion, right? And then in between you have all these different links, what you can think of them as simple levers that are connected together with hinge-like joints. So the biggest question that was posed by Franz Reuleaux, he was a German kinematician, and he's considered to be the father of modern kinematics, which is the area that I do research in. He asked this question as to how did he design it, right? And James Watt basically said that, he doesn't know himself as to how he designed it. Maybe he had a moment of eureka or whatever. But it is said that he was more proud of this mechanism than he was for the steam engine that actually he designed, right? So this is a very basic question. This is a question that I wanted to sort of work on and solve. So I approached NASA Science Foundation with a proposal to solve this problem, basically, ground up, figure out how do we design these kinds of mechanisms, right? So if you have a motion, how do we design these mechanisms? How do we decide their topology? How do we decide their dimension, right? So this was a big question, right? So now we are at a point where mostly artists design these kinds of things, not so much engineers, and this is where we want to change things. We want to make sure that the engineers have right kind of tools available to them to design these interesting mechanisms that are part of important machines, as well as mechanisms that go into the robots. So this is forward, like fast forward now, we're talking about 2018, 2019, 2020, in the last 3 years. My research is bringing together, 3 separate disciplines: machine learning, which is part of the AI, rigid body kinematics, computational shape analysis. So there are disciplines over here from computer science, disciplines from mechanical engineering that we are bringing together to solve, some of the outstanding problems in machine design area. And one of those examples I presented to you just a few seconds ago. And another interesting project that I've been involved with is designing and developing basically a design-driven robotics education platform, all the way from K through 12 and college students and beyond. And again, this is also a big story, long story that goes back 6 years ago when I was basically teaching a freshman robotics class at Stony Brook, and I was really perturbed that the students really didn't get much design experience putting together these robots. Okay, they were mostly focusing on the programming side, but not so much on how do you design robot motion. So when you look at walking machines or walking robots, the biggest question is how do you put together the walking motion? Okay, it's not less about programming the motors and things like that. So I've been working on developing this platform called SnapExo Design, which has been now funded by several NSF programs and SUNY Research Foundation and several other state organizations, which have sort of helped us develop this platform now. It includes the hardware. You can see these are more plastic pieces, which are very simple to use by the kids. And then we have the MotionGen app, which is what we will be sort of working with today. And then curriculum and learning material and professional development material for the students and the teachers and the like. Okay. So this is where you're seeing some of the hardware. Again, the hardware is all locally manufactured. This is all laser cuts. So these are high precision pieces. They work with off-the-shelf electronics. They're very intuitive. You don't need that many parts to put very complex geometries together. And it works with different kinds of materials. And it integrates well with our app also, as you will see shortly. Okay, so let me show you a little video. This is a video of a robot project that students in my freshman robotics class do, and this was done by a group of 4 wonderful girls from my class. This was part of the theme when they had to design a robot toy that would entertain a 3 to 6 year old child. Okay, so let me play this video, and hopefully you will get the audio as well. Let me make sure that I share the sound. Okay, so you will see examples of mechanisms and SnapExo hardware here.
When life gets you down, you know what you gotta do?
I don't want to know what you gotta do.
Just keep swimming, just keep swimming, just keep swimming, swimming, swimming. What do? We swim.
So the mouth is a 4-bar mechanism that is connected to a gear train, which is then connected to the servo. The gear train is used to amplify the torque of the servo and open up the mouth a little easier.
For the tail mechanism, we decided to work with a servo motor because of our ability to program the motor to go to set positions that would allow us to really create that wagging organic motion that we're looking for. And we just have SnapExo pieces creating the length of the tail, and to make that more fluid in itself, we connected each link by a rubber band, and that was chosen because of the restoring force, which would naturally cause the beams to snap back in a linear fashion.
For the body, we decided to build a box shape using beams that was covered entirely with cardboard. This was so that we would have the easiest access to the Arduino and breadboard while also keeping the bot lightweight for consumer usage.
So let's get to the MotionGen Pro. So this is our software, which runs in the browser currently. In fact, if you go on the App Store, you will find an early version of MotionGen called simply MotionGen. If you do a search for that, you'll find it. It's a free app, so you of course, welcome to download it. But our latest version runs inside the browser, so you don't need to really install anything. You don't need to download anything. You just need to have a computer with a modern browser like Google Chrome or Firefox. And this is the app that allows the students to basically design their own mechanisms for robot motion, okay? And this is where they understand how the geometry of the parts that are connected with each other result into a certain kind of motion that they might design, okay? At the same time, you can design your own custom shapes. You can design your own custom robot geometries, which you can laser cut and 3D print. So these are some of the new things that we have done in the app. The app itself can do what we call N-bar planar linkage systems. So they can include hinges. They could have sliding joints, and I'll give you a quick demo of that. But first thing you need to do is go to this URL called motiongenpro.appspot.com. So if you have your Google Chrome or Firefox browser open, then you need to go over here. If you don't have an account, then it will prompt you to create an account. So if you can do that quickly and activate your account, then we can move on to the next thing. So I'll give you maybe a minute or two to do this, to create an account. You will get a confirmation email in your inbox. Sometimes it goes into the spam folder, I've been told. So if that's the case, you don't see it in the inbox, then check your spam folder. Sure. So there is a question from Doug about the kits. Yeah. So the robot kit itself, the hardware part, I'm assuming you're talking about that, Doug. Robot kit basically has a set of what we call the plastic pieces, plastic parts, and connectors. Think of them more like a modern version of Lego. The only difference is that they're all planar pieces, so they're rather easy to sort of work with. They're all made in a high-grade plastic called Delrin. And then we have kits for elementary students, for middle school students, but it's the same hardware that works all the way from elementary to high school and beyond. So it's one sort of a what we call a unified platform, universal platform. Just the complexity of the parts sort of increase, the number of parts increase as you go up in the kit. And then when you get to the middle school and high school level kits, then you get electronics also. So you get microcontroller. It works with off-the-shelf microcontroller like Arduino and Raspberry Pi. So far we have it standardized on the Arduino. So most of our instruction material references to Arduino Uno and Nectar. So Jack is saying he cannot see it in the spam. It should be there. Okay, so Maggie says done. That's great. Okay, let me fix my share in the meantime. All right, I'll share my entire screen because I'll be switching between the presentation and browser. So let me make sure that I can do that. Yep, okay. All right. Samaya, are we good to go? Are we good to move on to the exercise?
How about we wait for like just a couple of more minutes?
Okay.
A few people are waiting on the activation email.
Okay.
And yeah, so it should be there. It usually comes in. It's usually the activation email comes in maybe a minute or two, but it'll definitely be there. Just hold on. Yeah.
Right. Okay, for some reason I can't see the chat anymore. Oh, okay, it's here. Okay, all right, so Dennis said done. Jack found it. All right, so I think
just a couple of people are left, so I think under a minute, I think they'll also find it.
okay. Right, so once you log in successfully, you should see a grid in the background. So what you're seeing right now on the screen in my presentation, that's something like that you should be seeing. Okay, so Jack logged in, so it looks like everybody is logged in now. All right, that's great. So we can move on to our first exercise. All right, so the first exercise is to basically create what we call a MechAvatar, right? So you guys know about digital avatar, and MechAvatar is my spin on a mechanism avatar. And basically, this is something that is going to represent you digitally today in a sort of a mechanism sense. And we will do this using what we call 2 RR serial link. Okay, so 2 RR serial links are basically like a serial robot, right? So what's a serial robot? Well, a serial robot is something that's an open chain, pretty much like my hand, right? I have a shoulder joint, I have an elbow joint, and then I have a forearm, right? So between the shoulder joint and the elbow joint, I have got my upper arm and I have forearm. So this is what we call a 2R, serial link or a serial robot arm, because I've got 2 joints over here, and each R is a revolute joint. Okay, so I mean, if you can put this Padlet into the chat, that'll be great. So I'm going to show you basically. I'm going to give a little demo of MotionGen Pro. Okay, and you just watch that for the time being, and it will be like a short demo. And then I'll give you basically this exercise to do, okay? And then once you have your result, you will basically post it into this Padlet, all right? So you take a screenshot, save the image, and then go to this Padlet, and you see a big plus sign icon at the bottom right corner, and you can click on that and upload it. Okay, so but before that, let me give you a quick sort of a demo of how MotionGen works, okay? So when you look at this interface, right, you see a series of icons. On one side, so on the right-hand side, you see these icons. These are what we call mechanism modeling icons. This is using these icons, you can model a mechanism, you can synthesize a mechanism. On the top right, you see icons that allow you to do transformation and selection. So you can take something, you can rotate it, you can mirror it, you can scale it, and those kinds of things. On the top left, you see what we call view icons. And there are different views supported over here. So if you take your mouse and you hover over these icons, so it will tell you a schematic view, it will show you what we call a kinematic view, and there's a SnapExo view. So essentially, you can design whatever you want. And then in the SnapExo view, you can see basically how that mechanism would come together using SnapExo hardware, okay? And there is something called freeform view, and this is particularly important for high school and college students who are trying to design their own robot parts. And so that way we don't restrict them to just using SnapExo hardware. There's a 3D view, and then you can record your animation, whatever you are playing. And this is what we call hamburger icon or the main menu. So if you click on it, you see the option to create new files, save files, open them. You can import an image, as you were seeing in my presentation. There was an image, and on top of that, I sketched something. You can export your geometry of the mechanism into different formats like PDF formats, format for 3D printing parts or laser cutting. This is where you can see multiple mechanisms that we have put in our library. And again, you can basically save them in your own account also, and they'll be available only to you. And then the settings. On the left side, you see a series of icons that allow you to basically design your own shapes and also be able to attach those shapes to different parts of the mechanism. Okay. So enough talking. Let me show you how we can put together something very simple. Okay. So the first thing I'll do is I'll basically click on this top icon on the right side called Draw RR Diet, and RR is, think of RR as just one robot arm. Okay, where the endpoints are revolute joints. So I click on this, and then I click anyone on the screen and drag. When I do this, basically I create what I call is an RR arm. Okay, this is just one link over here. All right. Now you see. There is the endpoint of this is highlighted, right? So that means that this one is selected currently, and I'm still in this mode where you can draw another RR diode. So I can go ahead and just click again close to this point, which is highlighted, and drag another location, and I get another RR diode or an RR link. And then I can click again here because this point is highlighted and go back to my original point. And if I do this, basically I create a triangular structure. And at this point, I think everybody here knows that triangles are, good things that go into the structures, right? So if I hit the play button, by default, this little green arrow shows you there is a motor connected over here. If I hit the play button, you see this entire thing is moving. Okay, so but this is one structure, and it is not very interesting to us because this is a structure. There is no relative motion between these three links, right? These three links, basically, they maintain their configuration, and the entire thing moves together as a whole. So in reality, this is just one single object we're talking about. So I'm not interested in this kind of a structure. Okay, what I'm interested in is a mechanism. And a mechanism requires at least 4 links, right? So here we have, 3 links basically, and what we need is basically a 4th link over here. So I'm going to press the undo button. And when I do that, you see my last action was deleted, right? Which was the 3rd link, okay? So at this point, what I'll do is, I want to show you something else. I can click on the select entity. So I'll go into the select mode if I click here, or I can just click on the canvas anywhere, and it'll go into the select mode. And I can select any of these points. So when I click on any of these points, they get highlighted. And once they're selected, I can click on them and I can drag them interactively. Okay, so I can do this. And now I'm happy with this location, let's say, all right, or I can move it further. What I want to do is I want to draw another RR diode or a RR link from this point. But this time, I'm not going to connect to the original joint. I'll just leave it here. And then I will fix this point, right? So for fixing it, we have this option called fixed joint, which is the 4th last option. I'll click on that, and now this point gets fixed. So now what I have got over here are 3 links which are allowed to move, okay? I've got 3 links that are allowed to move, and I can move any of these anywhere I want. So you can see I am doing this. And as I'm doing that, you can see the trace of these points emerging. So you can see the trace of this point is a complete circle. That means that this link can do a full revolution. The link number 4, on the other hand, can only do an oscillation about this point as the center, right? So let me hit the play button and see how this whole thing works. This is what we call the simplest possible mechanism, 4-bar mechanism. It's called a 4-bar mechanism because you've got 4 links here. Now you may be wondering as to where are the 4 links? I only see 3 links. 3 links are moving. The 4th one, which you don't see, is actually the ground link, or what we call the frame. So that link is the one that connects from this fixed joint to this fixed joint. Okay, so this is still a 4-bar mechanism. The link number 1, which is not labeled over here, is a ground link over here. Okay, so let's say I was looking for this kind of motion, right? Imagine, you want to take a can of paint and you just want to shake it, right? Because you need to mix your paint before you use it. You have a DC motor that can do a continuous rotation, but you need this kind of oscillation. Imagine attaching your paint can to the link number 4, and then link number 2 is connected to your motor, and as the motor is turning, the link number 4 is basically doing back and forth oscillation, right? So if you want to convert a complete rotary motion into oscillation, something like this would suffice for you, right? Okay, but generally this is not very interesting because in the end, link number 2 and link number 4 are still doing kind of a circular motion only, nothing more complicated, right? And, link number 4 is doing oscillation, but it's really not that complicated. Now, interesting motions actually come from the link number 3. So what I can do is I can click on the link number 3, which is what I call the coupler, because it couples the link number 2 and 4 and convert it into what we call a triad, right? So if I click on it, that link becomes basically a triangle. And this particular point of the triangle is something that I can move in the space. In this plane, I can move anywhere I want, right? Now imagine if I have something like this, right? I bring it over here. Now I have an interesting sort of motion curve for this point. And what is that curve? Basically, this point is going down and it's coming back up, right? So imagine I'm trying to design a robot, and that robot has to have a mechanism that's going to bring something down. Maybe it's trying to hit something. Maybe it's like you were going to attach a hammer over here, and there's a nail over here on the ground, right? You can sort of hit on the nail and come back up, right? Or you're trying to dig something through the ground. Maybe that's the action that your robot needs. You can put something like this together and then hit the play button, and you can verify whether it has the motion that you're looking for or not, right? So you get far more interesting motions from the link number 3 than you get from link number 2 and 4, because link number 3 does what we call a general sort of planar motion, right? So that's what we're doing over here, okay? Now, let me go to library, and I want to show you something. And I have put here an example called Dunkerfish, right? So Dunkerfish, if I open it, it basically is nothing but just a chamber, right? And again, I'll show you how we can draw these kinds of things. And I got a fish over here, and I need to move this fish because this fish is thirsty inside this chamber, right? So what I can do is, as you just saw, I can design a 4-bar mechanism. And right now you're going to do this kind of interactively. Okay, so, but I'll show you another way to do this. Now I'm going to turn the link number 3 into a triad, and I bring it over here. All right, and you see how, you know, I can have the path that I was looking for, right? You see the path I'm looking for? It's, if I can have this fish move along this path, I can have it go inside this water and come out, right? Now, all I need to do is take this fish and somehow attach it to link number 3, right? So I can do this. Now, how did I model this fish? Let me show it to you. So on the left-hand side, I've got this close curve option, right? And if you don't see it, what you do is you long press, because any of these icons that have a triangle shaded kind of a thing over here, you basically long press on it, and then you can select whichever you want. It opens up basically, all right? So this is a group of icons. So I can draw a closed curve, and I'm going to draw something that might look like a fish, and my drawing is not very good. Okay, well, it doesn't have a mouth. So what I'll do is I'll draw another, you know, shape over here. Okay, but that doesn't look like a mouth. So I can do what we call Boolean operations, where I can add and subtract and, you know, do these kinds of things. So I'll long press, do a subtract this from this, right? Now I got my mouth. Okay, I also want to have a little eye. So I'm going to draw a little circle, and I will do another subtraction from the fish body to this. And let me give it some color, right? Because I like colorful fishes. Okay, so I get something like this. So this is how I can model these kinds of shapes, okay? So what I want to do is I want to attach this fish to link number 3. So there is an option here called attach shapes to links. I click on that, select my shape, select my link, and now those two are attached. So when I hit the play button this time, see what happens. The fish goes down, and this tank is definitely not large enough. But now I don't like that the fish is crossing the boundaries of this tank and so on. So what I can do is I can change these parameters, right? So I can move these, and I can see in the real time how these paths are changing. So as I move these pivots, or as I change the link length, I begin to see newer motions appearing, or newer motion curves appearing. So this looks kind of what I might like to do, right? So imagine trying to design a robot or a machine that basically does this for you, okay? So there are a ton of stuff here, and I'm not going to go through all of these, but I want to show you very quickly as to how to design a simple 4-bar mechanism, and then convert the coupler into a triangle, design your own shapes, and attach those shapes to whichever link you want, okay? So this is what we call a closed loop mechanism, because essentially the loop over here is closed, all right? So let me delete this whole thing, and I'm going to show you now another kind of mechanism. I can reset the view by clicking on this icon. So this is what we call a 2R link, right? And this is an open chain. This is not closed because we're not coming back to where we started, right? So it's open. So this is pretty much like my hand is, okay? Now, of course, this is not going to be sufficient to move. You don't see the play icon here. That means that you're missing an actuator here. You've got one actuator at the fixed joint, but I need one more at the elbow joint. So this is the shoulder joint, this is the elbow joint. So I'll select this, and I'll click on this option called Add Actuator. And the moment I do that, I see now interesting curves emerging, right? So I see the path of this point. I can also select this point and say, I want to see this path, okay? And if I do that, I will see the path of that point as well, okay? And if I click on this play button, I can see how this point is moving along a circle, and this point is moving along, you know, this path, right? Okay, so this brings us to our, you know, first exercise, right? So what I want to do is I want to select the speed of this to be 3 RPM. I mean, actually, it's not 3 RPM, but it's probably for the sake of simplicity, think of this as 3 revolutions per minute. It's a different revolution unit over here. And this one is by default the same, but I want to change it. So I'm going to change it by increasing the speed and see, and I will make sure that this is a multiple of my base joint speed. So this was 3, and I'm making this to be 6. And I can increase it to 9, 12. And as I keep increasing it, I see interesting patterns emerging over here, right? And if it is a multiple of 3, and I will not go into the math of as to why this happens, but if it's a multiple of 3, then you will see complete closed and symmetric curves emerging, okay? So this is what I want you to do. I want you to put a 2R serial link together. I want you to specify the motors for both of these joints. This joint will be automatically specified. And then select the speed ratio, make this to be 3 and this to be a multiple of that, until you are looking at a pattern that maybe represents you today digitally. Okay, and this is your Macau chart. So I'm going to give you 5 minutes to do this, and then we'll come back and discuss more. All right. So go ahead and start doing this. So put a 2R serial link up and then attach the motors. And if you have any questions, feel free to post it in the chat. So Jack, you have to click on the joint in the middle. So if you added the 2 links, then you click on the joint in the middle where you can see my cursor, and then you click on the option to add the motor or add actuator. This is the third last option on the right side, but you have to first select the middle joint. Yes, so if your midpoint of the 2 links is selected, then you should see this option called Add Actuator. So those of you who are probably looking at the Q&A with a number of questions from somebody called Neil Purwar, that's actually my son who was in 2nd grade, and he's super interested in MotionGen. But he definitely needs help from an adult to make this work. So I'll do that later on. Ameya, you can just let him know that your dad is going to help you later. Okay. Doug, is there an option for us to be able to see maybe Jack's screen so that we can help him with this? If we can give our attendees permission to share their screen, then we can take a look as to what they're doing and maybe quickly just point out at the problem. So access to animate the image, you would have that animation pane available if you have the joints. You should see a play button in the bottom, but that would be visible only if you have the sufficient number of motors. So Maggie, did you put together this 2R serial link? I think it would be great if we can allow the attendees to maybe ask questions using their microphone.
Professor, if you could just show them the diode option and just sketch it once more on the side.
Sure.
In case they might have missed it before.
Okay, I'm going to start this process all over again. So first thing is you start with a blank screen, right? If you have anything that's not working, just press the delete button, everything will be gone. And then click on the draw RR diode, click anywhere and drag. Okay, and then do one more time by starting at the same location, the highlighted location. And this is what you should see. And of course, when you just have two links, then you're not going to see any animation options. So what you have to do is click on the elbow joint and then add an actuator there, which is the third last option on the right side. So I click on that, and as soon as I do that, then I see these curves emerging, and then I see the play button. And at this joint is selected, so you can change its speed to whatever you want. And as the speed changes, you see all these different patterns emerging. Yes, Neil is not happy. Okay, so Doug is saying he can bring him as a presenter, but cannot allow him to share screen due to security issues. Okay, all right. Okay, that's fine. Jack, were you able to solve your problem? Okay. All right. Okay, so clearly we're going to need a lot more time than what we have left in today's sessions. We have only 2 minutes left before the session ends. And let me ask Doug if how long can we really stay in this session before we truly have to wrap this up? Doug, do you have any feedback on that? By 20 after at the latest, so 6:20 I'm assuming. Yeah, okay. Yeah, okay, all right, so we have to basically leave by 6:20. All right, so let's see if anybody was able to complete this successfully. Let me see on the Padlet if anyone has put anything on the Padlet. Okay, I don't see anything here. These are all old. Maybe they are, but I cannot find it here because there's so many from other sessions. Okay, all right, so because we don't have that much time left, so what I'm going to do is, of course, we're not going to have time to do all of these exercises that I have here, but these slides are available to you nonetheless. And you can definitely go through these exercises on your own. In fact, at the very end of this presentation, there is a link to which you can click, and there are a few sort of tutorial videos that I have posted, which show you basically as to how to use MotionGen Pro. There are 4 videos. Each video is about 6 to 7 minutes long, so it's not really that big. And they basically give you an introduction to how to use MotionGen Pro. So what I have shown you here is probably just one of those videos. So you can definitely learn more over there. But what I want to show you in the remaining amount of time is a few examples that we have over here. Okay, so if you click on the library, open library, and you click on different examples over here. So for example, radial tire. You will see a mechanism that we have put together. This is a mechanism for designing the tires, basically, that can, or think of them as wheels that can sort of increase in size or decrease. So if you hit the play button, you will see as to how this whole thing works. So these are variable diameter tires we are talking about, right? So they can shrink and they can grow, and you can model these kinds of mechanisms over here. Okay, There are other, interesting examples over here. Let's say we have an octopus here, I think. Oh, let's look at the pest control. So this is an automata kit project mechanism where you can design your own mechanism and then you can sort of put them together using SnapExo hardware. So there are lots of interesting examples in the library, which I would encourage you to explore by clicking on this option, Open Library. But another interesting thing that I want to show you is the synthesis option over here. And this is rather new. This is what uses machine learning and kinematics and computer vision to solve the synthesis problem. So what I have shown you so far is just the modeling part where you put a mechanism together and then you look at the motion curves appearing. And if you're not happy with them, then you can tweak the mechanism parameters and get new paths. But this is the true synthesis option where you can actually click on the draw path option, and then you can basically draw a path, okay? And when you draw this path and you let go of your mouse, the app is going to synthesize different kinds of mechanisms where a certain point of the coupler will trace that path for you, right? So you can see this is a humongous mechanism for a tiny path. So it may not be a very good choice, but you can click on this light bulb icon and then you can go to the next one. So that's number one, that's the second. And this is the third one. And this is what we call a 6-bar linkage system, which is slightly more complex than what you've been seeing so far. Let's look at the number 4. Okay, yeah, this is a good one. So this is the basis for designing a walking robot. So, if you want to design a walking robot, you want to have a mechanism, this is the kind of trace for a foot point that you'll be looking for. So something like this can be integrated into a frame. And if you have 4 of these, you'll essentially have a quadruped, okay? And we have actually put together something like this, which I can show you since we don't have time to look into this. So this is one mechanism, right? And this is our sort of a hardware using which you can put this together, okay? And this is a video of how this whole robot actually works, just using a single motor. So you can see that you have 2 4-bar linkage system on each side of this frame. And the frame is really very minimalistic over here, just a plate and all of these battery pads and breadboard and everything is sort of mounted using our own connection system. So it doesn't really require any screws, any tools. The SnapExo hardware allows you to physically prototype these robots, and MotionGen Pro allows you to design the mechanisms behind them. And if you are happy with what you design, or you want to figure out whether this is a good design or it's the correct design or not, you can take a picture of your mechanism and bring it back into the app. And I'll show that to you in a minute. So what you can do is you can click on the image option, and I put some of these images in your shared folder. So this is an old pattern drawing of a dough kneader. So this is the mechanism for kneading the dough. So you can sketch right on top of it. So imagine this was your creation. This was your own invention, your own patent, and you wanted to verify whether this was the way you've designed it. You can verify that. And let me just connect these two together. So this I will turn into a triangle link, and I will bring this point over here, and voila, I can see that I will get about the same path. So if I hit the play button, I will see how this works. So let me just increase the speed because 3 seems to be way too small. Oh, for some reason I can't do that. Okay, that's fine. So you can verify this is what we call completing the design cycle. All right, so I want to respect the time that is allotted to us here. And Doug said we could go on to 6:20, and this is 6:20. So we have to stop here. But I have shared the slides with you. There is a little survey at the end of this presentation, which I would, of course, like you guys to fill out. If we will do some sort of random lottery, I don't know how we will do it. I'll speak to Amia about that. And if you're selected, we'll send you a robot kit, at no cost. All right. Okay. If you have any questions, my email address is in this presentation. You can reach out to me. Thank you, everyone, for attending our workshop, and apologies for not being able to complete it as we planned.
Yes. Thank you. Thank you so much. And we really look forward to your feedback, and have an exciting Maker Faire ahead.
All right. Thank you. Bye, everyone.